All right. Okay. All right. So let's just start off the basic info. So today I'm just gonna go over again the basics. I think Jordan basically explained all of them. Um, and uh, and then also say a little blurb about the various projects, which hopefully the mentors can fill in. I made these slides today. Okay. Okay, so first off, it's 2 months. It's going to happen in summer one, so May 8th to June 27th. Um, $2,000 monthly stipend. And yeah, so this year we'll up it to 2,500 if you're in person and you're like not doing anything else. So that's like your main thing. So on the website, it's just called full time. Can't really do math full time. So, you know, full mind, not full time. Okay, and then just like general idea is, we'll put you in small groups, maybe around three, and then focus on work on like a research project supervised by a mentor. Some of them are grad students, some of them postdocs. We're hoping some faculty this year, but not really. Okay, but and so I'll say a few more words about that. But I think like being part of being adult is like making deals and like evaluating them and like, oh, that's a good deal. Oh, this one's like that's a terrible deal. This one's too good to be true, right? You get those scams about like the job opportunities, right? Right, like yeah. So this is like we're paying you to like learn math. It's ridiculous. Um, but so for baseline, it'll be 20 hours of work probably a week. Um, but hopefully these are all kinds of things where you get what you put into it. So um, and yeah, so we've had previously like we've had participants who are like in co-op or doing some internship at the same time. Um, I don't know. I would still be okay with that. Like, some are pretty strong applicants for probably doing other stuff too. So, and then this year, as opposed to recent years, this will be in person. So, um, yeah, so we'll have snacks, depending on how many people we have. We'll book some rooms, quiet spaces, loud spaces. I want to roll in some extra whiteboards. So, but then, if you have something else going on, then we'll try to organize it so you can like try to participate remotely. But of course, you're gonna take the hit. And the application deadline is like next week. So, all right. So, what the heck is math research? So you're basically just doing this over and over again. Um, and no matter what I'm gonna ramble about, like I just want you to cycle between it's over and we're back. It's like somehow you become a mathematician after that. Um, all right. So, uh, okay, these are basically my slides from last year. So I think there's kind of three components in my view for like doing math research. First, you got to learn a ton of stuff, um, and kind of understand, what problems people care about. It's a social scene, right? No one cares what you're working on. No one's, you're not going to get very far. So yeah, just understanding the scene. So you have to learn some of that background material. Um, and then, once you learn enough, you need to be able to come up with plans. Um, and hopefully solve some problem. And a lot of that involves the kind of more exploration, computing stuff, maybe identifying smaller things to solve. You also have to talk to other people. Um, and finally, we implement the plan. I mean, this isn't like, you're not running any experiments. You just have to write the paper. And a lot of times, like writing is really painful because that's when you're implementing your plan. A lot of things don't work out. So, um, and also when you're like even just giving some formal presentation of what you're working on, you kind of realize a lot of the things you did are uh, you failed to implement them. So yeah, like this might seem a little surprising if you're not used to it, but like really like writing is the worst. That's when you do all the work. Okay. um yeah, and I think this is probably pretty applicable to, you're just doing math in real life. um and then within each project, they'll probably weigh each of these components in various amounts. So, a lot of them is just learning stuff. Some of the projects have like, a lot of computation involved or even coding. Some of them don't even involve open problems, and that's okay. I think my experience last year, the open problems don't really make it much better. It's like just don't feel that fun. Okay. And yeah, overall, I'd like to have all participants to experience like these sorts of steps. So maybe not like take a problem and put it to the end, but get a flavor of that, right? So you got to learn stuff, compute things, be able to talk to people, and kind of witness the inconsistencies in your thought, just like right in front of you. Okay, it's over. It's over. It's over. Okay, and then it's only for 2 months. So you got to think about what this means. So basically, all you have to do, there's a final paper, at least 10 pages amongst your whole group. There's a final presentation, about an hour. Yeah, I think we'll still do 20-minute preliminary presentations halfway through. And your mentors will, they'll guide you through background material, both during and prior to the program. Try to get an overall plan, because it's just 2 months. Like if you don't have a plan, you're just going to waste your time. Help you get unstuck. Sometimes you learn more when you're stuck, but again, you only have 2 months. So, and then during the presentations or the course of writing the papers, they'll actually like give you concrete tips. And it's only 2 months. So like, don't think about this necessarily as, oh, in 2 months, I'm going to like do all this stuff. Like, think about it. It's maybe helpful to think about it as the start of something. So I was kind of hoping if more faculty were involved, like this could be a good bridge if you want to do like a more substantial like capstone project. No faculty involved. So, but like think about, oh yeah, I can learn this thing. Maybe that'll help me like learn this other thing later on. Right? So don't think about this program on its own. All right. Any questions? Oh, yeah. Okay, that's what I just said. You ever write slides and then you forget what you wrote on them like 2 hours later? Yeah. Okay. So, so any questions about generalities? This is like the important stuff. Everything else is just math. Like, sure. All right. Okay. So, these aren't under consideration. They're already considered. So, yeah. So these are projects we've approved so far. One on p-adic numbers, chemical reaction networks, affine algebras and conformal field theory, and then Schwartz functions and compactifications. I'll say a little blurb, just stuff I like made up. And then, yeah, we want to have at least one more project. So, all right. So, and so the mentors had to submit a proposal. Those are posted on the webpage. Okay, so p-adic numbers. What's going on here? Yeah, maybe part of this is like, maybe it'll help you read the proposal a little better. So, okay, so the starting point is that power series really rock. Anyone who says otherwise is wrong. Okay, so that's my stand. Freedom of speech. Okay, so the main idea. So you could just take like the decimal expansion of a number, and then calculus. So you're like, okay, that's a power series. So 1/3 3 repeating, and then how do you like solve for those threes? And you could do this with any 10. You could replace 10 with anything. Note that like big negative powers means like you're really small, right? Close to zero. And then, yeah, how do you actually solve for these numbers? Okay, so think of each like negative power of 10 as some sort of marker for how close you are to zero. It's like 1/3, it's like somewhere over here. Yeah, like you're on the highway. 0 is, I don't know, like Indianapolis, and then you have these highway markers along the way. So, okay, so how do you find those coefficients in the decimal expansion? Well, okay, um, basically you just find a number between 0 and 9, that you find the biggest one, multiply it by, that power you're at, and subtract it off. You just do that consecutively. So like at the first step, okay, 1/3, the most I can subtract off is 3 over 10, right? It's like 10 minus 9 will just be 1/30th. Yeah, you subtract off another 1/10, you're off in negative land. Okay, so that's that. So 1/3 is 3 times 1/10 plus 1/3 times 1/10. And then you can already see the repeating pattern, because now you repeat that for 1/3, this 1/3 again. You're gonna get the same thing, but then you like stick it in for the red 1/3, and that's like for the 3 keeps on going off forever. Make any sense? Sure. This did not make sense to me like last night at 10 p.m. So all right. Okay, that's how you can see this repeating pattern here. Okay. So let me do something similar but completely different. So for a prime p and a rational number, a over b, doesn't really matter what a and b are. This will find this valuation that's a nu, so p, to just be like the biggest power of p you can pull out from the numerator minus, from the denominator. So I just pull out p's from the numerator and denominator until what's left over doesn't have any p's in there. Right. So for example, if I take this 5 valuation for 1/3, that's just 0, because so the valuation is the power, right? So there's no powers you can pull out here. Okay, if I go for it, u sub 3, that'll be -1. Okay, so let's pretend that having high powers so fix a prime p and pretend that having high like this valuations at p means you're closer to 0. So like you're tired of driving to Indianapolis, let's spice it up, replace the signs, right? It's okay. So now, and this at first glance, this sounds really stupid, because like here, right, these are kind of like big powers of 5. Right, back then we were doing like big negative powers of 10, like small numbers. Okay, but what if we just try the same thing? So what do I mean by this? So at p equals 5, let me just subtract a number between 0 and 4. Yeah, so that like the result will be we'll have like a higher evaluation for 5. So it sounds a little tricky here, but like, so 1/3, I start with 1/3. If I subtract off like just 1, you'll have like -2/3, right? And that has valuation 0 for 5. If I do 2 though, then that's the -5/3 over there. I could pull out a 5 now. So boom, I did it. That's 2. And then -1/3. So not exactly 1/3, -1/3. So it's not like last time where it repeats itself. And so now let's focus on that -1/3. Okay, you could try 1, you could try 2. It's not going to work. You try 3, I subtract off 9 over 3. I'm going to get like -10. Right, over 3. Now I could pull out a 5 again. So so this step here, this will be 3 times, oh, that should be a 0. Sorry about that. It's here, and then later on I'm going to like collate this. So I'm going to stick this in here. Okay, and then we're still not repeating, but we get to -2/3. Okay, now 1 will work. Be like 2 minus -2 minus 3 is -5. Yeah. So and now we're back to some sort of repeating pattern, right? We're back to here, which was what we had over here. Questions? It's something you could do. Someone just made, actually a bunch of Germans just made this up. So like all the names here are super German. So okay, so we've gone back to -1/3 and you can repeat. Yeah, so you'll have some sort of, I'm gonna collate, like stick this in for here, stick this in for here. You kind of collate this all together and you get this ridiculous expression. 1/3 is 2 plus, and then I have the odd powers of 5 here. Here are the odd powers, so even plus 5. Those all have coefficient 3, and then the even powers after the constant term will have coefficient 1. Okay. Like this is ridiculous. This is a divergent series, right? It makes no sense. So the idea behind p-adic numbers is just to view like higher powers of p to be really small. The more 5s you get, the more closer you are to Indianapolis. And okay, so basically in this sense, just pretend that like the magnitude of p is less than 1. So you can just do, so these would converge, these power series. And then, okay, if this kind of power series would converge to here. That's the 15. You add it together and yeah, you get back to 1/3. Okay, so this is ridiculous, right? That's the end of it. Okay, yeah, so this is something you can do. Yeah, but I mean like sorry, so the idea of the p-adic numbers is somehow like, first off, like this is about number theory, like you kind of allowed to do these analytic methods in number theory, and kind of yeah, so if you have like rational numbers, how about this? So wow. Okay. So for example, if you want to show that like this equation has no solutions over the integers, one thing you could do is just look at this mod various primes. So give you just like 2, 3, like you'll cover this. On the other hand, like it seems naive that like maybe if you have a solution for mod primes that you can like lift this to like a solution, like an actual integer solution. And yeah, these kind of p-adic numbers, you can try to solve equations using the p-adic numbers. And it turns out if you like solve them for all primes, you can actually lift to like an actual rational number. So really some weird stuff. Okay. But yeah, so the mentors for this one aren't here, but like they're also like Hunter, he messes a lot with the computers and he'll like have you code a lot of stuff. So yeah. Any questions? Yeah, so a lot of these project overviews, I didn't make this heading here, but like a lot, I was making this and I felt a lot of regrets. Like my regret for this one was this is the first time I actually computed a p-adic expansion. I've been like seeing p-adic numbers for like years. I never actually computed it. Okay, so in this project you'll get to like do that more often. All right. The second one is Elon's project. Feel free to chime in. You just send me some slides. So
Yeah, I didn't have anything prepared. I can use Word. It's mine.
oh, I have something in the bottom. Yeah, feel free to.
Someone else has a class here because there are people standing outside and there's also an instructor standing outside.
Do we have class? Hi there, class.
Oh man.
Okay, to be fair, in 2 minutes, you have the old group back.
Oh, that's true. Yeah, we would have that one. This is exactly what we mentioned. It was not what it was.
Yeah. It was great.
No.
No, it's 7:30. I mean, so sorry.
Oh no, that's fine. This is okay. Yeah, so next project's on chemical reaction networks. I saw a talk about these things like 10 years ago. That's all I know about this. So Elon sent me some slides. But there is a point I want to make. So I do have like a personal experience seeing math with this. Okay, but like you just like talk about like a bunch of, think about atoms going to molecules and then just you have a list of reactions, and then you just want to keep track of the quantities of like the various stuff you have. And you can get this set up where, yeah, they give you dynamical systems. Let's say give some more detail on that. But yeah, so it should be reaction. So Elon sent me a really great example. That was good. I couldn't read yeah, Wikipedia was not very helpful. So for example, if you just have like this list of 2 reactions and 4 things here, you'll just keep track of like the 4 flavors of things as a function of time. And then like, oh, this is just the time derivative. So it's just dt here. And then you just model this change over time in a pretty simple way. So you just have a matrix, and then which I guess records somehow these reactions. And then so for each reaction, you have this function R, these R functions that I guess have to do with the rate of change or the rate of the 2 reactions. So and so if you look at this, it's like all the complexity is like in here. You can make it as complicated or as simple as you want. And correct me if I'm wrong, but like a lot of times when these like ODs show up in like applied areas, like these never are like super duper complicated. Like and that's not a dig. It's that you don't really necessarily need to be like super like analytically sophisticated. It's that it opens it up to a lot of tools. Like you could just use linear algebra. So the talk I saw was on like polytope combinatorics and like not really algebraic geometry, but like combinatorial algebraic geometry. So I don't know where Elon's going to take things with it, but I mean, like it's like
there's something called a monotone dynamical system, which is a dynamical system that occurs in partial ordering. And one thing to be able to look at is when these systems
so you're saying like when partial ordering like with respect to the quantities here, or okay.
So yeah, those are like Rn.
Yeah.
Each one.
Uh-huh.
And so you might ask when this dynamical system, as it changes over time, they maintain some partial ordering. And oftentimes the reaction rates, they're often like polynomials. Hence algebraic geometry sometimes comes up. But for the monotone system, we often assume there are a class of reactions. No specific reaction, but they're just like their partial derivatives are positive. We assume some other things, but no specific form. So yeah, so that's a little bit.
Yeah. And computers.
And yeah, you can program.
Computers, yeah. I mean, like these polytopes, right? This is like computers, man. Okay, so well, yeah, so that was really good. Yeah, I mean, this makes it really clear what the complexity is. Okay, so all right, affine algebras. So these are like certain like infinite dimensional symmetries. Now, like why would you care about that? Like why would you make your life difficult? There's really an origin story though. Like people didn't do this starting because it was fun. So yeah, so all these symmetries kind of appear in finite dimensional settings. Okay, you didn't like just make them up. Yeah, especially with regards to like solutions to differential equations. So here's like a really baby example. Actually seems a little silly. Okay, so just take functions on a circle. So, okay, what functions on a circle do you know? Well, you could view like sine and cosine as functions on a circle, right? They kind of repeat themselves at 2 pi. I guess the length is 2 pi, and you just kind of glue them together. That's my low effort graph of sine. Actually, it's neither of those things, right? Oh, yeah. But sine negative it. Okay. And yeah, so there's a whole finite dimensional situation. There's an intrinsic symmetry here, right? Because like they're on the circle, and like this n is just kind of measuring how symmetric you are. So if you're like big N, then you're like really symmetric. So all right. Where's the diffie Q? So these are eigenfunctions for the second derivative. Yeah, well, we'll get to affine algebras at some point. So, and then these nice part is these are like actually the basis of all functions on the circle. Okay, not all functions, but But I mean, like when you compute Fourier series, right? That's what you're doing. You're writing a function on some wave, and you're like doing this. Yeah. All right. So let's just do some extra nonsense here. So throw in some complex numbers. I could repackage all this in terms of these exponentials. Yeah. All right. So we have this like intrinsic circular symmetry. And then on these solution sets, you have on the solution, on these special functions here, there's an emergent. Yeah, so these infinite dimensional symmetries just kind of are extra, But in this case, yeah, so that's what I mean by emergent. Okay, maybe it seems so you can have like vector fields on a circle act on these functions. By that I just mean like an operator of the form like function on the circle times the first derivative. All right. And then since sine and cosine and thus these e to the in, these exponentials form a basis of functions, you can just write everything as e to the in. E to the in theta times d theta. And then if I just define this new variable z, well, oh my goodness. This is d theta. So if you think this through, acting up by this vector field on, for example, like e to the im theta will be the same as just like multiplying using this operation here. Right, so the d theta brings down the m, right? And then you boost up by plus n. And here you just bring down the m, and then but then the power of m, the power of z goes down by 1, so you need to like recompensate. That's what this thing is. So all right, so whatever, that's like some geometric nonsense, but then then you just hide it, you can shove it away. You just define this letter dn to be like this operator, and you compute the commutation relations, and it's like pretty nice. And so now, okay, it's not vector fields on a circle, it's just a bunch of letters satisfying relations. That's called algebra. So yeah, it's all like there's a lot of geometry involved. There's even some physics, but it's also just all algebra. So, if Anadel has a physics background, if you keep on saying physics, just like make it algebra, man, right? So, yeah. Okay, so that's an example. Another one you can do is just take n by n matrices and then have with values and like kind of like function values. You view this as like a function, on something valued in matrices. On the other hand, you could also handle this as just a bunch of symbols satisfying some relations. And in this case, these sorts of symmetries show up. The big story, I don't know if Anadel will cover it. Who knows? But this is like one of like the poster. So this is my regret for this project was I didn't learn about affine algebras with regards to this stuff here. So so these act on like certain like solutions to certain equations that describe standing waves. You should look them up on YouTube.
I do not have any kind of cover in solid one, but I can.
Well, like I said, right, this you get the program, it's only 2 months, so it doesn't have to be a full story. We need to start with something.
Do you have first slides for my project?
No.
You want
Yeah.
me to say something?
Yeah. I started making these at like a 4. Like I didn't have any time.
So affine algebras, as John mentioned, is an instance of infinite dimensional symmetry. We have a special name that these objects we call them infinite dimensional. There are many types of infinite dimensional algebras, and it turns out that with very special physical systems, the algebras are symmetries of those physical systems. We refer to those physical systems as informal field theories. They are very important in physics, in statistical physics, string theory, with quantum field theory. They have extreme elements. So what we are going to do, there's like a practical goal and then an idealistic goal that I have. The practical goal is that we understand the theory of a little bit about the theory of affine algebras, a little bit about these conformal field theories, and see how they relate to each other. The idealistic goal is that we can go a step further and
and try to understand a special correspondence between those conformal field theories, these special Lie algebras, and something known as we're going to use the name that would be initially a Chern-Simons field theory. This relationship between the special class of Chern-Simons field theories, which were used to compute knot invariants back in the 80s using quantum field theoretic techniques, which led to the person who did that winning a Fields Medal, among other, like he did a lot of other work, but this was a critical piece of the work that he did. We're going to try and investigate the relationship between these conformal field theories / affine algebras and these this Chern-Simons field theory. If we somehow get to that point, I will be very proud of whoever is. This story is mostly clear to me with like some exceptions, so I'm using this project also as a motivation for myself to clarify the story for myself. It is part of my thesis. So yeah.
Yeah. Sweet. All right. The final thing.
Any questions?
Oh. Yeah, and what he's talking about is different from this physical thing, which is kind of wild too. Like, yeah. All right. So Short's functions. This is the thing I'm like, so well, I'll talk about my regret for this project. But so yeah, and Ahmad, please chime in anywhere. So for example, like, so this will be like talking about functions on a compactification. So what's like the first compactification you learn? You know, your 1-point compactification of the plane, right? So you have the plane, you got the Illuminati eye in the top, and then everything gets glued at point of infinity at the eyeball. Okay, so like when you do like geometry or topology, you're just like, okay, yeah, I get that. But like if you actually like think about functions, like a lot about real analysis and like why it's frustrating is like, right, you want to practice safe function theory, right? So like, okay, you can't differentiate every function, so we need a definition for that. You can't integrate every function. We need a definition for that. You can't integrate every power of an integrable function, so I need a definition for that. And it's like, oh man, right, all these definitions, right? But it's to be like really safe with your operations here. And so if you think about like, yeah, let's just say in this case, like try to describe functions on the sphere in terms of functions on the plane, right? And you already have this zoo of sorts of functions, right? So like, that's like, I see there's definition of Schwartz functions, like, oh, they just want to like take derivatives or something. Yeah, so these are some sort of like there's definitely like a sort of, I think, some sort of craft or philosophy of how you like define these sorts of functions, right? Like you want to like naively just take functions and have them decay in a certain manner at infinity, right? Then you could put it together, evaluate it at like the eye, the Illuminati eye on top. And in my perspective, it's very technical, but that's what Ahmad does quite well.
I don't think actually it's
Yeah.
super technical. So I'm doing a paper with my former advisor, and one part of that paper is very fun. It's very actually low level, like it's like a very in the level of knowledge, basic knowledge cross function. If you know a little bit about manifolds, actually you don't need to know about manifolds. I have to cover that. So what I'm planning to do, I'm actually trying to show that basically certain known functions that you actually see in Fourier analysis, you have a cosine, for example, which we're gonna define, cover what that means, what we do about them. And there are type of functions on Rn, for example, that if you multiply them with a polynomial, they're gonna still vanish at the infinity. None of them, they limit none of the infinity. And that holds also for the derivatives, to all the derivatives. So if you multiply with a polynomial, it's still gonna hold. But the thing is that at infinity for us in certain situations can mean something good. For example, for a plane at infinity, you can add that point at infinity to your manifold, to that plane, add it to that plane and get actually a sphere, smooth manifold, but known as a sphere. And basically the Schwartz property gonna translate into that function to vanish at that point, and all of its derivative also vanish at that point. And that's equivalent. That's been observed by Schwartz himself. But the thing is that this is actually known to be true for a bunch of other manifolds too. But the thing is that there is no literature and all that. So what I found is that during my calculation regarding what I was doing, known as deformation to the normal cone, it is really not known that even for a basic example of projective spaces, like very basic example that every undergrad in math that take a course in topology knows about. And that's statement is true. Actually, I proved it I had to prove it in my paper because there was nothing in the literature. So I was thinking, give it as actually the project. And if in case your the student project come before my paper, actually like my paper can cite the paper too. So it's a bonus for the undergrad. So you know what I'm saying? Like that's my grand plan. And it's not going to actually I'm not gonna cover that index here. I don't know why you say
Oh, no, it's like the motivation
Yeah,
though. It's not about, yeah.
yeah.
No, you're just gonna do it index there in
I
2
feel
months.
like something different,
Yeah.
but
Yeah.
it's just a one part of it which motivated my work basically.
Yeah.
And I thought it would be very amazing on the grant project. So you don't need to know much. I will cover like I will dedicate like first 2 weeks covering differential topology for those basically attendees. And we're gonna cover 2 books actually in 2 weeks. You're gonna see it's going to be quick, but it's not difficult. It's not this. Like if you know topology, basic topology, you can understand it. If you know manifolds already, that would be a boom. Like it would be even easy. So it depends. Okay, but yeah.
Thanks so much. Yeah, like you do all these like things in like topology, and you're like, what are the actual functions on it? And it's like, I have no idea. Yeah, it's like
You
I
gotta
didn't know. It's like in like lens spaces and like you know.
Exactly. I want to see
Yeah.
a bunch of examples that I don't even. I have like a general conjecture,
Yeah,
which we're gonna get close to it, but not exactly. But
yeah,
we can prove a lot of examples out of it.
Yeah.
Really.
yeah. This is more to do with my regret on this project. So so like a cool thing I think is really cool from a distance though is like analysis on manifolds. Like why do you want
Yeah.
functions on you want to do analysis on manifolds? And like it's super cool. So like so yeah, these index theorems that you can talk about where basically you have like dimension of some solution set to some distinguished differential equations on some manifold, roughly speaking. And it's like equal to some like topological invariant. So like the most famous instance of this was Tia Singer index theorem. And like Tia was just computing these topological invariants. There's no reason that they're whole numbers. He like goes up to Singer, he's like, what the heck? Like, why are these always whole numbers? They must be counting something. Oh, they're dimensions of some, some vector space. So I took like a reading course in grad school on a Tia Singer index theorem without like knowing like any of this kind of analysis on manifold stuff. And like, it's amazing how long you can like make a professor think think that you know stuff. I got nothing out of the reading course because I just did not have any background. So I think this would be a great opportunity to learn this kind of stuff. So yeah, probably you should not cover index theory in
No,
2
definitely
months.
not.
That's my professional advice.
Like a low level.
Yeah.
Like,
Yeah.
learn about
Yeah.
surfaces, for example, of projective spaces and how to write code. That's what you're gonna do. You're gonna be able to write code like that system. It's very easy actually.
Yeah. And so yeah, I'd even say it's not even so as you said, it's not just analysis and topology, big deal as well. Right. They could cool. That's all I have.
If anyone has any questions, please pose them now. Raise your hand and hopefully Josh can put them forward. When do we hear back on decision? Like, or what do we expect to?
Probably like first week of April. Yeah.
So I'm a first year undergraduate student. I don't have a lot of research background.
Yeah.
A little bit worried about writing a personal statement for the application. What would you suggest I write about it? Or maybe I'm a second year student. So maybe I've taken some classes, maybe have some professors I've talked to at least, but not necessarily an independent work.
I mean, I think like so like last year when we were kind of evaluating applicants, so like coursework is, I'm not gonna lie, it's pretty important. Like that's like you want people to have, and the more background you have, the more things we can put you in. So kind of like that. But then on your personal statement, yeah, if you're particularly interested in any project, then please put that down. Like we ultimately just want everyone to kind of fit into something. And yeah, it's like like in your first year without much coursework, I mean, you should try to apply anyways. And yeah, if you have really any interest in any of the projects or just any experiences that aren't on your transcript, please bring that up. But hey, I guess I have to say, like, the coursework is kind of important. Like, you know, if you like did an internship somewhere, I don't know. Well, I don't know how helpful it will be. So because sorry, it's like almost 8 o'clock. I'm rambling. Yeah. Any other questions, I guess? Yeah. So yeah, just I'd say, yeah, address the projects. Like if you just want to make sure you fit in. So like that's kind of what the coursework is too, right? It's not just like, oh, you have to go over these hurdles. Like we just want to make sure you fit in. Right. So oh yeah. Mhm. Questions. Something I should have sent an email, but so if you've done RU before, you know, you're still welcome to apply again. Yeah.
Should we submit a transcript or a resume, or can we submit both?
You need to do both. Yeah, unofficial transcript isn't it? The official, yeah. Mhm.
I'm gonna add something briefly. Just raise your hand if you've done this before.
Oh, no,
Okay, so
Elon's done it, right?
Oh,
Yeah, yeah. I remember scrolling through the webpage and I saw your name and I was like, man, this guy's been in grad school for a long time. I was like, no, he wasn't a participant. Yeah.
So I guess my point is, so there's 4 of us here, and there's also other people who have done this before elsewhere.
Mhm.
So like, if you have questions, but like either you're maybe too shy to ask them now or whatever, obviously email Josh, but like also feel free to reach out to any of us.
Here's the math club Discord, we can put an announcement there.
Yeah.
With contacts for people who have done this.
Yeah.
If there are no other questions, we're gonna wrap it up. So, yeah, great. Thanks for coming.